Who gets to introduce this? Mark? Organizer?
Well, well, as organizer, I'm very happy to welcome Fred Diamond, who will give a speech, give a talk on
Galois representations in automorphic forms was what I was asked to talk about.
Well, please do.
So to do that all in 1 hour is maybe kind of ambitious. I'm not sure exactly I'm pitching this right, but maybe it'll be review, maybe it'll be I don't know, stop me with questions or comments or heckling or whatever. So I'm going to talk about Galois representation first. So what do I mean? I just mean homomorphisms. From Galois to the GLN of R. So there's just mean the Galois group. I'll take a separable closure. Characteristic 0. So here F's going to be any field. But those we're really interested in are, let's say, Q, or maybe function field, or maybe completions, or finite extensions thereof. And R will also be any, well, let's say field, especially classical setting, complex representations, but probably more productively static representations, or maybe characteristic Galois representations. And oh yeah, I meant to add the bars later. So finite extensions of QL or FL, or may as well just pass to the algebraic closures. Or maybe I want any ring, like ZL. Or maybe I want any, say, complete local Noetherian ZL algebra. That's the board. Lopsided. And some of these rings have topology, and then we want to have continuous representations. Profinite topology. Something like Galois, finite extensions. Galois extension. Okay, so examples. Well, argument representations. Finite extensions at Q. The GLM of C. Which we are thinking of as a representation of the absolute Galois group, GQ by just surjection here. And L-ladder representation, first example. L-ladder from a character, denoted by chi-L. And I guess I just want to assume that L is not equal to the characteristic of F. And we'll factor through the automorphisms. Let's say when we join all the L power roots of unity. So I'll write that as a UL to the infinity. This is inverse limit of Galois roots. Let's call it the n power torsion. The nth roots of unity. And this injects into, so haven't finished constructing the character, but we know this injects into, each of these injects into z mod L to the NZ cross. So mod L to the NZ cross, which is ZL cross. So here we have an injection. And see bad planning first forth. Maybe I want to think of this also as being contained in well, divided. And of course, this is GL1. I'll state it down. So GL1 of ZL, but maybe I also want to put QL contained in QL and QL. Okay. So then, of course, we also have 11 modules. Curve over F. I'll continue to make this assumption. And then we define TL of E by taking the L to the N portion. So same thing we did here, where you take the L to the N portion of GN, you take the L to the N portion and a little curve. And we know this is isomorphic, it's like L wasn't characteristic, it's isomorphic two copies. Choosing a basis is isomorphic to Z mod L to the NZ squared. Just as an abelian group. So this is equal to L squared. And this comes with an action here at GF. So we get GF2 of ZL. I want to think of this. QL and then QL and QL bar. Make things more uniform later. Okay, so where this encodes a lot of information about E. Example here. And we assume that P doesn't divide the conductor of E or equivalently the discriminant. And let's also assume P is not equal to L. The discriminant. Then what we've got here is now our representation, I call it rho EL. Here, rho EL. Then we know that the points are defined over an extension which is unramified at P. So let's just look initially, say, 2 of C mod L to the R. And then these factors through some finite extension, just call it L sub n, and n. So the image is, however, for some finite extension where this Ln is unramified at P. And so the L-adic representation is unramified at P in the sense that it factors through an extension which is unramified at P in the sense that all the finite sub-extensions are unramified at P. So maybe I should say rho E bar L to the n. And mod L to the n representation here, again, an example now where R is Z mod L to the n, falls in that category. So rho L is unramified at P. And so there's a well-defined conjugacy class of Frobenius in the image. So rho E L of the Frobenius at P in each of these, and then the inverse limit is a well-defined conjugacy class. So we can talk about the characteristic polynomial. And this turns out to be x squared minus AP x plus P, where AP counts points mod P on the elliptic curve, which is, we can talk about since P doesn't divide the conductor, we can talk about the elliptic curve. It has good reduction at P, there's an elliptic curve over finite field FP, and AP counts the points related to the number of points, so AP is P plus 1 minus the number of points. So where AP P plus 1 minus the number of points of E, right? Okay, so a lot more is true. There's the Shafarevich criterion, which tells us that in fact, if the extension is unramified, then the elliptic curve has good reduction at P. So conversely, rho E L is unramified at P. Again, I'm assuming P is not equal to L for now. Then P does not divide the conductor. In other words, P has good reduction at P. Ridiculously small message. They're all like all the long pieces of code. Use. I'll save this then.
I'm trying to try.
Yeah, so we have this, and more is, yes, important fact here, which I forgot to mention, is that this, maybe I should use colors. Is that this is independent of L. So now we can vary the L. Again, I assume that L is not equal to P, and the characteristic polynomial that we got here was independent of L. And right, what I wanted to say is that there's a more general independence of L statement. That's following. So to formulate it. But so now I want to allow P to divide the conductor as well. So what I'm going to do, instead of just looking at Frobenius, I'm going to look at the restricted decomposition. So I'm going to choose embedding the Q bar into QP bar. So that's going to give me and embedding of the absolute Galois QP into Q, just by restriction. I guess it's maybe it's not obvious that it's injected, but it is. So then we also naturally have by restriction to the integers of your finite extensions and reduction mod P. We have this natural map. And we know what this Galois loop is. It's generated by convenience. Topologically. So this is just a Z hat. We can define inside here W. I'll just write image, right? W P be the pre-image convenience here. And then I can consider the restriction WP, very group at P. So this is the definition. Does this make sense if I just write that? Defined as the pre-image. So now I can restrict to WQP. So rho EL restricted to WQP is independent of that. If E has potentially good reduction. If E has potentially good reduction, at P. So these are all landing in QL bar, but you think of them as well, they're defined over Q bar. And this is equivalent to the image of inertia being finite. So we can, well, maybe I'll make a more precise statement later after I deal with this type of what happens if E has multiplicative potential and multiplicative reduction. You see, there's no hope of this being true. So what if E has potential multiplicative reduction? Multiplicative reduction. So for example, if E has split multiplicative reduction, and we can say pretty much exactly what the Galois representation, what the Galois representation looks like by the theory of the K curve, rho EL, with respect to some basis is a cyclotomic characteristic on the board, chi L, 0, 1 star, where this is infinitely ramified. Notice these are unramified at P. So this has a tame quotient, a copy of ZL, where this is landing. Which you can see from taking L power roots, which we construct from L power roots of the uniformizer. Right, so then this is what's my theory of the curve. So you see there's no hope of producing something which is independent of L. In Brilliant's idea of associating, so that's why it's called a Galois representation. By which I mean other ways to do this, but so sigma in M, where sigma is a representation of Alatic usually. Where now we're going to ask for continuity, where now we give this the discrete topologies. So continuous with QL bar given the discrete topology. We can put a more general field here. And N is, well, think of this as an automorphism of n-dimensional vector space instead, and think of N as a no-code operator on it, but just think of it as an n by n matrix. So, so nilpotent and satisfying what to write sigma of P and is 3 and sigma of Phi, where Phi is any lift of Frobenius here.
So the fact that it's potentially multiplicative is why you have a continuous representation. The discrete thing kills the image of the inertia as finite. Is that the idea?
So,
and then the n is this upper corner.
Yeah, so let me just say what happens in this case, and then I'll say what the sigma on the are in this particular case, and then more generally, it'll just be a twist of that by some finite quadratic character. And yeah, so then the n will replace this that's in the corner. So Phi is a lift of Frobenius. Any lift for Phi. Right, so for rho L, now the sigma is just going to be the direct sum. And n will be 0, 1, 0, 0. And then, well, more generally with the potentially, it's just going to be a twist of this. So for potentially multiplicative, we get it. Just twist by a character. Quadratic character. And then you really do get something which is generally independent of L. So I'll call this the associated Galois representation. You can make this construction for any L-adic representation. In fact, you can associate it with the Galois representation. W3 of rho E L really is independent of L. So the resulting is independent of L. Be careful about saying defined over Q. I'm not sure you can write down G up to Q, but defined over Q bar. There exists a sigma m as above. If Q bar instead of QL bars. Such that when you base change, when you extend scalars to QL bar, you get this sigma n, and that works for all L.
You don't have to worry about the prime P.
L not equal to P.
But when we think of this as a sort of a mixed motive, I mean, we have this like an extension of the trivial.
Yes, yeah, you can think of it as coming from. Where you interpret this n as coming from monogram. Okay, so now what if L equals P? So, and this is the touch theory. The way this works. On pen defines big rings, Chris, be semi-stable, ROM, that. And these have some additional structure. Well, they all have that. So these are all QL algebras, QL algebras, topology, have a G, sorry, not P is equal to L, so I'm not going to worry about it. All right, QP algebras. I mean, here I want to think of it as QL algebras, but I'm also going to. So with GQP action, GQP, there's a phi acting on P Chris, there's an N acting on BST, there's a filtration, beta ROM. Yeah, that's right, Bill. Then for any continuous, row from GQP to GL and some QP bar. Will always be defined some finite extension. In fact, instead of writing it, I'm just going to QP bar. And let's think of it on P. Then we can find the Chris of B by tensoring with B Chris and taking variance. And this will be finite dimensional. It's finite dimensional. Oh, right. B Chris GQP. Here it's just QP. And in fact, the dimension is the most n.
The row is going to be in QP instead of QP bar.
Right, yes,
Or I guess you could get undimensional, but the invariance tensor QP bar.
yes, right. Yes. QP bar tensor QP here. And here,
But you could also put the invariance before you tensor.
I could, yes, because, yes, so,
Because you don't
yes,
want to.
GQP is not acting
Exactly.
on the first factor, so, yeah, it'd be better to think of it this way. So, in fact, the dimension is and then we say that the representation is crystalline. And when it's crystalline, if equality holds, and notice here we so because of the compatibility of the structures, here we have a phi as well. And we can similarly define VST and the ROM with the additional structure. So this will come with an N as well, and this will come with inflation. You lose the B and it gets the N.
What was the problem with the answering QP bars?
I didn't understand.
So, right, so, I mean, maybe it would have been better just to put a finite extension E here.
Oh, I see. There's a,
And then, or what did I use for R? And then I put your E here. But you don't want the GQP action. So GQP is acting trivially here. It's only acting here. It's just it's just some coefficients that are.
We come out.
Oh, sorry. So this is E linear, right? The representation is E linear.
Oh, I'm sorry. Oh, okay.
Right?
Oh, okay.
So it comes out here, but not here.
Yeah, yeah, okay. Oh. So you think of these sort of complex multiplications.
Yes, yeah.
but
It's
if
just,
you just take the Chris G Gal invariant, that is QP. Or is it?
Yes.
Yes.
That was
Yes.
that was the thing.
No, these guys are not going to
What, sorry, what do we do?
think differently. No, it's terribly confusing.
Once you work over a fixed finite extension QP, you could just make the N bigger.
Yes, that's right.
So
Yeah, you could in fact just talk about the dimension over QP in that case.
I just thought there was a problem with the Chris Gal invariance being QP, and then suddenly when you tensor it's QP bar, you get QP bar.
It's okay. It's kind
Got
of.
Yeah, ignore, sorry about the bars.
No.
Okay.
Fine.
Right, so where am I? Right, crystalline, undefined. Crystalline, semi-stable, Durand, and well, I haven't really because I've left Fontaine's rings here as a black box. And let me just say what happens. For example, if n equal 1, then rho is crystalline. So if n equals 1, rho is crystalline. If and only if it's unramified, or you're switching to inertia, is a power of the cyclotomic character. Let me write it down. Rho restricted to the inertia at P is now chi P is equal to chi L to the n for some integer n. In this case, it's if and only if something stable. What the ST is for.
If you take for N, yeah, integer, which is not, it's not.
It's not true that it's crystalline. That's right. And then Durand, if and only if it's finite order times chi p to the n. So rho restricted to P is finite mu psi chi p to the n for some finite order. You could do this, and maybe that's the next thing I was going to do. No, that's not the next thing I was going to do. I was going to go back to the example of elliptic curves, and yeah, sorry about the E there. That was a bad choice. But so E an elliptic curve. So now for n equal 2, E an elliptic curve. Say over QP, elliptic curve over QP. Then rho EP is always the wrong. And it's crystalline if and only if P has good reduction at P. Semi-stable. Oh, maybe I should say Durand is equivalent to potentially semi-stable, where potentially means in these constructions, replace QP by a finite extension. So semi-stable, if and only if P has semi-stable reduction, multiplicative reduction, semi-stable. And notice in this case, we have phi. So in this case, phi as characteristic polynomial, the same as before, and it's gone x squared minus apx plus p, except my normalizations are wrong. This is really corresponding to the geometric Frobenius. So phi inverse that has characteristic polynomial x squared minus apx plus p. So more is true. Since E is always potentially semi-stable, that when you do these constructions over a field over which over finite extension of QP, or you have semi-stable reduction. Maybe because of time. Oh yeah, I should mention one more thing. So the D Durand in this case, D Durand of this rho E is isomorphic to the Durand homology. QP, whoops, maybe I should say QP bar. That's what I've done. If I've really gone to that, no. Oh, that's a really helpful. That's why you have that. Okay, anyway, H1 to round. 2p bar, except I think I've got the filtration shifted wrong because of normalization issues because they use the tape module rather than the homology. So there should be a shift here. I guess the shift is by -1. Or you could put a tape twist this by the inverse of the side of the common character to get a representation whose D to ROM is canonically isomorphic to H1 to ROM. And from these constructions, if you do these constructions, say over L, so if you take D semi-stable over L of this rho EP, meaning take TP of E, tensor with BST, and take the GL invariance for L containing QP, over which E has semi-stable reduction, such that E has such that E acquires semi-stable reduction. You have the data that's needed, because this is also going to come with an action of Gal L over Q, and it'll have a phi, and it'll have an n. And from this data, you can get a Wegelin representation. I'll just write WD, just say WDP of rho EP, which will be a Wegelin representation.
But how do I get the N just using the algebra?
Right, so it's just the n, it's just the n, it's just the n on this.
And the phi comes by just pretending it's crystalline, and that gives you the phi. Is that a sum n or something?
It gives you phi.
Wait, this also the BST also has a phi?
The BST has a phi, yes.
Oh, okay. I'm sorry.
And it will also be isomorphic to, this will also be isomorphic to D to ROM of the representation. Okay. Right, and so now this sigma n is the same as before. This really is independent of that. That is.
L is P.
Now L is P, but we got this. What I'm trying to say is we got the same L as before. Sorry, not this, we got the same sigma n as before. Same sigma n as for all L. Okay. Yeah, so I want to move on to say something about automorphic representations in the title. So say where this is going. So this all generalizes to say Q, replacing Q by F, a number field. You could replace the E by an abelian variety, or more generally any variety. X, and considering the atomic homology of X now over bar is Q L bar coefficients. So. Height module. Be consistent with, so this would be H1 twisted by 1. So this would be H1 of P F bar Q L bar. Hence, we're just like one character, a twistation. On outside. And so what's it's good for? Well, you know that that it's still true that the number of points. Maybe I want to assume that now X is smooth and projective. You can write the number of points and show exactly what generality. Say these things in the number of points, which is what point formula is really characteristic polynomial of Frobenius on these representations, L functions. Definition. So then L of some rho S would be the product overall P of LP of rho S where LP of rho S. So I should also say L-adic realizations of motives more generally than this. And then LP of rho S determinant identity minus rho on invariance passed to an F, I should say RV from V norm V to the minus S all inverted. So then you can talk about special values, which is really related to invariance, arithmetic invariance of whatever motive is using this representation, state conjecture. And prove that these L functions also come from automorphic forms. So, say a little bit about automorphic forms. That I put a 1 for Galois representation, so I'll put 2 there. So modular forms. Usual first example. So I want to find the space of modular forms, but this weight k level n, so these will be certain functions. The half plane satisfying invariance properties with respect to congruence of root m 0 of n. So if you have an F in here, it has Fourier expansion with A and B dot. By the invariance under 1,0,1. You also have on this space, I can also talk about the space of cusp forms. Heck operators. Say TP, broad times P, whose effect on the Fourier expansion. So TP of some A n equal to pi I n call. is some a n p e to the 2 pi I and tau. I want e to the k minus 1 times some a n e to the 2 pi I n p tau. And then what it means for the elliptic curve to be modular is that there's a modular form every e over q is modular in the sense that there exists an f in S2 and 0 and p such that the AP of f is equal to the AP of e, where the AP of e was as defined before, and the AP of f is the Fourier expansion. So this is for all times p, and I should have said, I guess, since I said that for all p, I should say that this term is only for p not divided n. So this is Wiles to the Wiles. Something Taylor. But the way it's proved is that rho EL is isomorphic to rho FL for some Hecke eigenform F. So the F that's here is in fact necessarily a Hecke eigenform. So for some Hecke eigenform F as above. So then what is rho FL? We have our representations from forms. So consider x not of n. So upper half will be like n 0 of n. So this is in fact an algebraic curve over Q, not just over C. And you can take its Jacobian to play 0 of n, or the Jacobian of x not of n. So now this is going to be a variety over Q. So you can make the same construction, you consider its Tate module. So like it's a Tate module VL. Yeah. Not confused with the back operators. Tate sub L of J0 of n. So this has an action of, let's write T for the algebra generated by these operators in the endomorphism ring. So I'll write T for the algebra of endomorphism generated by the collection of T for all primes P. And then you have an action of P here. But you also have, since this was defined over Q, you also have an action of PQ here. And in eigenform, you have a Hecke eigenform. A little bit of algebra tells you that this gives you a homomorphism from T to C, but in fact to Q bar. So F is an eigenform. This gives you theta sub F from T to, well, a priori to C, but in fact to Q bar. And I want to think of Q bar in the fixed invariance of Q bar into Q L bar and C. And if you just take this and tensor with QL bar, you get a two-dimensional representation, and that's your rho FL. So V sub L tensor T QL bar is two-dimensional. And this is on rho FL. And this is just a particular case of Langland's reciprocity conjectures. So modularity of E which associates, let's start, certain irreducible representations of E, L, and A to rank n motives over Q. I don't really know what this means, so I'm going to take the L-adic realizations and get instead compatible families of Galois representations. So there will be collections rho L, and maybe I should say certain compatible families. I'll make this more precise in a moment. Not, maybe not. So rho L, G Q to G L N of Q L bar. Okay, so let me try and so let me start here. And first of all, I'm going to replace this instead. So I can just take one member of the compatible family. And just consider rho L from GQ to GLN. And now I'm going to say geometric rho L from GQ, and that's going to tell you what this certain means here. GLN of QL bar. The compatible means independent of L, in the sense that I was explaining before, that the associated Vega-Lean representation is independent of L for all P. Geometric just means, so certain, just as geometric. Geometric means unramified outside a finite set and de Rham at L. So unramified outside some n, or outside some finite set, and rho L restricted to GQL is de Rham. The certain here is Well, first of all, automorphic, in the sense that it arises from L2 of GL and A mod GL and F. And there's an algebraicity condition, which is a condition on, so I should say pi here, because such pi's will always factor as restricted tensor products over all primes P. And this is a condition on pi infinity. And then what characterizes this bijection? Yes. So this is conjecture. So this is all conjecture. This is also, so any such geometric row L should fit into should be part of a compatible family. So this you can think of as Langland's conjecture, or Langland's conjectures, and this is Fontaine-Lazar. And this composite here, this composite bijection is Fontaine-Lazar-Langland's. Just to give you an F. And let me just say briefly what the characterizing property is supposed to be. So here you can restrict to GQP and get a representation, well, get a Vaugeline representation, which is like WD sub P. So you get a n-dimensional Vaugeline representation. And I need one more certain here, which is just Frobenius semi-simple. And here, you just take irreducible admissible representations, admissible being a finiteness condition. Of BL and of QP. So this is just sending pi to the factor of pi p. And this is the local Langland correspondence, which is a theorem. This is a conjecture, and it's a theorem of Harris, Taylor, and Young. Let's see. So the GLN here can be replaced by any reductive group in principle, but then this is just becomes more conjectural here. And this encodes, for example, so the other thing that I would have said is how to get from a modular form to a pi, which you would do just by taking, say, the limit over all n of spaces of modular forms, and this would inherit an action, well, a priori of SL n of the Adels, but you can turn it into an actual GLN of the Adels, some modification. And the Heck operator, the AP of F would correspond to the P. And for example, principal series here would correspond to just direct sum of two characters here in some nice way, but I better stop. Okay.
Are there any questions?
Yes.
Correspondence. You're
Yes.
supposed to have some L function.
Yes, exactly. Yes. So yeah, and so this is
That's what
a particular case. And so yeah, the matching of the local factors in the L function is inherited. So this respects local factors at all. So the factor that I wrote down here matches what comes out of the cycle. But you can't see everything just from the L function. There's more data encoded, at least locally, there's more data encoded in this correspondence, which sees the ramification.
So this is saying that if any positive function is essentially maybe this.
What is the Hasselbalch L function?
Just take it right here.
Yes. Yeah. And so there are lots of results in this direction. Yeah, there are lots of results in this direction, but the results going the other way are much more sparse.
So when you said that you were filtered by the GP module, you get this beta lean representation. So the action in the Vey group, I mean, it seems like you want, maybe you can say a bit more about how you get the action in the Vey group.
Yeah, so you need the interplay between the Galois action and the phi, which I'm probably not going to be able to.
Oh, okay, so it's a bit
right down on the fly.
Yeah.
Yeah.
You want an
It's
answer
the input is the. So there's this finite ramification in the Galois action, which you combine with the phi, which is telling you Frobenius.
And you need to like.
And there's a semi-linearity as well.
Yeah. That's practical. Do you have to choose a splitting of the exact sequence defining the Vey group, or you don't have to choose that? Because it seems like you have an action for Frobenius, you have an action for Nernst.
Yeah, so what you get is independent. Yeah.
Okay.
You choose and it's independent.
Okay.
Yes.
The question is, I'm sorry, it's very technical. When you express the Langlands conjectures or inductive groups, you treat the Langlands dual.
Yes.
What is its variance?
What is
its variance? Is it covariant or contravariant?
it? Is
Or not?
no. So that's part of Langland's functoriality, and it. Yes.
So the question is, I have two retractive groups, G and H, and a morphism from G to H. What does it induce on the Langlands duals?
Yeah. You can answer.
No, I mean, so maybe it helps to sort of review the role of the Langlands dual. It should be a record that it should be the target of rho. So if we have a map from G to H, then actually we have a map from G to H. No, it seems like the possibilities.
So the two, so to answer, if I'm going to try and do it on my feet, then I'm going to think about two examples. One is base change, and the other is symmetric power functoriality. And so what happens in those situations? So symmetric power functoriality goes from GL2 to GLN. And your row, your two-dimensional row will become its n symmetric power. So hopefully that's going to answer the question.
Yeah.
So
In that case, they're equal to their duals, right? Langland's dual.
yes,
GLN,
yes,
right?
yes,
It's just-
yeah.
Okay, so.
So it's GL2. And here we have the Langlands dual is GLN.
So then, I mean, if they're equal to their duals, you kind of know how the minus go.
Right, yes,
You know that there can be a map from GLN to GL2.
right.
Can't go any other, certainly.
Yes.
So
That too is.
Yes.
Can I ask a question about the thing you crossed out there? Not really. You crossed it out, but this word geometric. So is it expected, the conditions there? It's DRAM plus some other things. Is it part of this is expected, whatever mode it is, that every such geometric Galois representation really does come from somehow from geometry, from
That's the really kind of amazing and surprising thing about content-based architecture. Is that every I mean, it's, already it imposes a strong. It's imposing some condition on the norms of Frobenius eigenvalues, which and that's so which is obviously not true just for the local Galois representation, but the fact that it's coming from something that's global is somehow what's miraculously imposing those conditions.
Can I ask a really stupid question? Well, that's.
I'm sure it won't be.
No, I mean, you talked about the basic case of elliptic curve and bad reduction, you get some extension. Thing, and that seems to be motivating. And then you explained the role of leading in. And suppose that I have, I mean, those seem to be the simplest representations. The cube by cube kind of thing. But I want to think of them really seriously. So I have in particular a complex odd structure of all these realizations. So I have a complex odd structure, which gives me an extension class, C star. And now how can I get the n at P from a complex, a non-zero complex number, which is telling me the extension as a hot structure? How do I play that game? These have to be the simplest possible such thing. Sure.
Yeah, and I'm not used to thinking about it from the point of view of pod structure, so I'm not going to be able to answer.
I'm gonna.
Yeah, well, sorry.
I think we have to get another talk, 2 minutes. So I think we have to thank Fred again for beautiful talk.
It was supposed to start till 10:15. I thought it was supposed to start at 10. Is that right?
Yes, yeah. No. Yeah, my talk starts at 10.
Oh, that's a relief. I thought it was really running into it.
Yeah.
You're okay. You're fine. Not to worry.
Anyway, you can't change your talk now.
Give it again.